In section 4.5, we'll cover how to predict the products of acid-base neutralization reactions and how to write the ionic and net ionic equations. Our learning outcomes were covered by the textbook author's goals for this section. But we also want to add some terminology from section 5.9 to describe titrations. Let's begin there. A titration is a laboratory technique for determining the number of moles of a substance dissolved in solution. The standard solution has a precisely known concentration, and the volumes of the standard solution and the sample are both carefully measured. Using that information and the mole ratios from the balanced chemical equation, one can calculate the sample's concentration. The titrant is typically dispensed into the sample of unknown concentration using a burette so that the volume may be measured precisely. The volume of the sample is measured precisely as well before pouring it into an Erlenmeyer flask. A few drops of an indicator is used to signal the end of the titration when the moles of added acid equal the moles of base in the flask, for example. If you'd like to see a titration in action, take a minute to watch the video in figure 5.16 from the textbook. In acid-base reactions, hydrogen from the acid combines with hydroxide from the base to form water, while the remaining ions form a salt. Note that both acids and both bases shown here are strong acids and strong bases, respectively. Acid-base neutralizations aren't very exciting to watch unless you've added an indicator. While no visible changes occur in the reaction mixture, heat is released. In the top example, a weak acid is added to a strong base. What products are formed? When the acidic proton combines with the basic hydroxide to form water, you're left with acetate and sodium. What is the neutral salt formed? Which coefficients are needed to balance this reaction? In the next example, we have a strong acid plus a strong base. What products are formed? When you add the acidic proton to the basic hydroxide ion to form water, you're left with barium and perchlorate. What is the neutral salt formed? Which coefficients are needed to balance this reaction? We can write ionic and net ionic equations for acid-base reactions just like we did for precipitation reactions. To be successful, you'll need to remember the strong acids and strong bases, which will be written as separate ions. Weak acids and weak bases will be written as aqueous molecules. Let's look at the details. A strong acid, strong base reaction will give a total equation that yields water and a salt. The net ionic equation writes all reactants and the salt as hydrated ions in solution. Note that liquid water is a molecule and is not written as ions. The net ionic equation will result when we cross out the spectator ions, chloride and potassium. What results is the net ionic equation that you will get every time you have a strong acid, strong base reaction. A weak acid, strong base titration results in a slightly different equation. The weak acid, HF, is written as a molecule to reflect the fact that it's a weak electrolyte. The strong base is written as separate hydrated ions in solution, as we see that K+ is the only ion that is a spectator in this reaction. For this reason, the net ionic equation will be unique for every weak acid neutralization you encounter. Here's one for you to try. First, identify the acid and base as strong or weak. Next, write the ionic equation. Finally, write the net ionic equation. Pause here to compare your work to mine. Here's another one for you to try. First, identify the acid and base as strong or weak. Next, write the ionic equation. Finally, write the net ionic equation. Pause here to compare your work to mine. As always, I'll leave you with the parting thoughts of the authors, first from section 5.9, but also from section 4.5. Take notes, then allow the video to finish playing so your scores transfer to Canvas.